Think about the seemingly invisible forces that shape our world and drive countless industries, the way air flows around a skyscraper, the movement of liquids in a chemical plant, even the intricate flow of blood within our bodies.
Yeah, absolutely. These are all governed by the principles of fluid dynamics.
Right.
And understanding how fluids, both liquids and gases, how they move, isn't just some theoretical exercise. It's fundamental to so much of our daily lives and absolutely essential for innovation across a huge range of engineering and scientific fields.
And that's precisely what we're diving into today. We've got a stack of fascinating material here, everything from in-depth academic papers to practical guides on computational fluid dynamics, or CFD.
Right.
Our goal in this deep dive is to really unpack why understanding fluid dynamics matters so much, to get a clear picture of what CFD is and how it's used, explore its diverse applications, and maybe even glimpse into the exciting future of this field, especially with things like machine learning coming in. Ever wonder how a massive airplane manages to stay airborne? Or how engineers design a new artificial heart valve to work seamlessly inside the human body? Fluid dynamics, and increasingly the powerful tools of CFD, they hold the answers. Okay, let's unpack this.
Let's do it. So, starting with the basics fluid flow itself, we're talking about the motion of liquids and gases.
Mm-hmm.
And while you might immediately picture, water flowing through pipes or wind blowing across a landscape, the underlying principles are at play in countless other scenarios. You see it on the grand scale, like weather patterns.
Yeah.
In the vital circulation of blood within our own bodies, even in something as, seemingly simple as how heat moves around when you're cooking.
Right. But where this really takes center stage, as the sources you showed emphasize, is in the world of industry.
Exactly.
Take aerospace, for example. The very shape of an airplane wing, the aerofoil, that's a direct application of fluid dynamics, isn't it?
Absolutely. Engineers use CFD to simulate airflow, whether it's, high subsonic speeds or even supersonic over these designs.
Yep.
And that allows them to really fine-tune the shape for maximum lift and minimum drag. Doing that purely with physical prototypes, it'd be incredibly expensive and just, take forever.
Yeah, I can imagine. And it's not just about things that fly.
Not at all. Consider the cars we drive. Automotive engineers are using fluid dynamics and CFD constantly to sculpt the bodies of vehicles, making them as aerodynamic as possible.
Cut down on drag.
Exactly.
Yeah.
Reducing drag translates directly into better fuel efficiency and performance. One of the sources even mentions this thing called the Ahmed model.
Oh, yeah.
Yeah, it's like a simplified, standardized car shape they use as a benchmark.
Mm-hmm.
Helps them test and compare different CFD software, different turbulence models, understand the really complex airflows around vehicles.
Ah.
And they're also using these tools to look inside the engine, investigate and optimize what's happening right inside the combustion chamber of a piston engine.
It's amazing how far-reaching it is. Then you've got biomedical science.
Oh, absolutely critical there. Understanding the flow of fluids within the human body. CFD is being used as a virtual prototyping tool for incredibly delicate surgical procedures.
Like what?
Like carotid endarterectomies. That's cleaning out arteries in the neck. It allows surgeons to visualize and sort of optimize the operation before they even step into the operating room.
Wow.
It's also vital for understanding how blood pumps function, analyzing blood flow in arteries that are narrowed or stenosed or have stents put in, even studying the airflow dynamics in our nasal passages.
So the insights you get are just invaluable for developing better treatments and maybe less invasive medical devices?
Precisely. Less guesswork, more targeted design.
Okay. And the chemical and process industries, I imagine fluid flow is pretty central there too.
Oh, heavily reliant. Understanding how fluids mix, react, flow through equipment. Your sources talk about simulating really complex processes like heterogeneous and slow dissolution in packed beds. They even give the example of a blast furnace in steel making.
A blast furnace. Okay.
Yeah. So CFD helps engineers optimize the design of mixing tanks, reactors, all sorts of industrial equipment, leading to more efficient and, cost-effective operations.
And the list keeps going, right? Environmental concerns.
Definitely. Using CFD to model how pollutants disperse in the air or water, think of the plume from a cooling tower.
Right.
Or optimizing the placement and efficiency of wind farms to harness renewable energy better.
Yeah.
Civil engineers use it too, designing water treatment plants, even doing pre-construction analysis of massive storage tanks to make sure the flow and mixing are right.
Power generation, nuclear safety.
Yep. Both rely on CFD. Increasing efficiency in power plants, ensuring safety in nuclear reactors. It's really everywhere.
We could probably spend the whole time just listing examples.
We probably could. Design of efficient heat exchangers, whether they're compact or have these intricate tube arrangements, that's heavily informed by CFD, looking at heat transfer and flow. Even something like ventilation systems in buildings.
Really? Like office airflow?
Yeah, ensuring comfortable airflow. Or preventing contaminants spreading in, say, a train cabin. Submarine design uses CFD for validation studies around the hull. Tunnel ventilation, looking at pollutant dispersion and the piston effect from trains.
What's the piston effect?
It's how a train moving through a tunnel pushes the air ahead of it, like a piston. CFD helps analyze that.
Gotcha.
Then there's studying combustion, like how flames behave. Even understanding how fluids interact with flexible structures, like our airways deforming when we breathe.
Wow.
And industrial processes like continuous casting of metals, understanding multi-phase flow of molten steel is critical there. Even designing steam ejectors. It just goes on and on.
Okay. So it's abundantly clear that having a solid grasp of fluid dynamics and being able to use tools like CFD offers some really significant advantages across, well, almost everywhere, it seems.
Huge advantages.
We're talking about evaluating designs virtually, optimizing performance without building tons of physical prototypes,
Right.
driving down costs and timelines.
Precisely. CFD provides a level of detailed insight into fluid behavior that's often very difficult, sometimes impossible to get just from physical experiments. It lets engineers explore a much wider range of design options, different operating conditions, and importantly, it plays a crucial role in meeting regulatory requirements. Companies can show their designs are safe and efficient using these comprehensive simulations.
So here's where it gets really interesting. What exactly is this powerful technology, CFD, that lets us do all of this?
Right. Let's get into the nuts and bolts. Computational Fluid Dynamics.
In a nutshell.
At its core, it's using numerical methods and algorithms to solve and analyze problems that involve fluid flows.
Okay.
So instead of building a physical thing and testing it, CFD relies on generating approximate numerical solutions on a computer that mimic how real-world fluid systems behave. Think of it like doing virtual experiments.
So it's almost like creating a digital twin of a fluid system that we can then poke and prod and analyze.
That's a really good way to put it, yeah. And as your sources emphasize, the main goal isn't just about generating, pretty pictures of flow patterns, although those can be helpful.
Sure.
The real power is in gaining a deeper, more quantitative understanding of the flow behavior within whatever system you're studying.
And that understanding then lets engineers and scientists make better decisions about design or optimization or figuring out problems.
Exactly. Informed decisions.
And it sounds like it's become more accessible recently. The barrier to entry isn't quite as high.
Definitely.
Yeah.
The increasing availability and, frankly, user-friendliness of commercial CFD software has been a huge factor in its widespread adoption across industries and research. You don't necessarily need to be a hardcore coding expert anymore to use CFD for many common applications.
But it's not meant to completely replace physical experiments, right? There's still value in actually building and testing things.
Oh, absolutely. You're spot on. CFD and physical experiments are best seen as complementary tools. They work together.
How so?
Well, CFD can provide a vast amount of detailed data, look inside places you can't easily put sensors, and explore conditions that might be difficult or even dangerous to set up in a lab.
Okay.
But physical experiments provide that essential real-world validation data. You use experiments to calibrate your CFD models, make sure they're accurate. As one of the sources points out, simulations often give more comprehensive data than experiments and are invaluable for understanding the why behind what you observe experimentally.
Got it. So they feed into each other. Okay, so if someone wants to actually do a CFD analysis, what are the typical steps? What's the workflow like?
It usually starts with a really clear definition of the problem you want to solve. What's the exact geometry? What are the fluid's properties? What are the flow conditions, pressures, velocities, temperatures?
Okay, define the problem.
Then geometry creation. Building that digital representation of your system in the software.
The digital twin part.
Exactly. Then comes a really crucial step.
Mesh generation.
Meshing. What's that? You take the fluid domain, the space where the fluid flows, and you divide it up into a huge number of small interconnected cells or elements. This mesh is basically the grid the software uses to perform calculations at all these discrete points in space.
That sounds like it could be tricky, especially for complicated shape.
It absolutely can be. It's kind of an art form sometimes. And the quality of that mesh is absolutely critical for the accuracy and stability of the solution. A bad mesh can give you garbage results, basically.
Okay, so good mesh is key. What's next?
Boundary conditions. You need to tell the software what's happening at the edges of your computational domain. Like, What's the fluid velocity coming in? What's the pressure going out? What happens at the solid walls?
Setting the rules for the simulation.
Precisely. Once all that is defined, geometry, mesh, boundary conditions, fluid properties, the CFD software gets to work numerically, solving the governing equations of fluid flow across all those mesh cells.
The heavy lifting part.
That's the computation, yeah. And finally, post-processing. You take all that raw data the solver generated and turn it into something useful, visualizations like plots, contour maps, animations, and then you analyze that to understand the flow behavior and extract meaningful insights.
And this whole process allows engineers to, say, test 5 different wing designs virtually without having to build 5 physical wings.
Exactly. It enables the efficient evaluation of alternative designs. You can systematically explore a whole range of operating conditions, tweaking those dimensionless parameters. We talked about Reynolds number, Mach number, Rayleigh number, things like that.
Right.
And this virtual prototyping capability, as it's often called, is incredibly valuable, especially in fields like biomedical engineering, where making and testing physical prototypes can be super time-consuming, expensive, and sometimes raise ethical questions.
So what does this all mean? It means CFD is just an absolutely essential tool now for understanding and manipulating fluid flow pretty much everywhere.
Couldn't have said it better myself. It's transformed how we approach these problems.
You mentioned the software solves the governing equations. Can you unpack that a bit? What are those?
Sure. The fundamental laws that dictate how fluids move are described by a set of partial differential equations. Collectively, they're known as the Navier-Stokes equations.
Okay, Navier-Stokes.
Yeah. And they're based on fundamental conservation principles. Conservation of mass fluid isn't created or destroyed. Conservation of momentum, which is basically Newton's second law applied to fluid particles. And conservation of energy, the first law of thermodynamics for fluids.
That sounds mathematically intense.
Oh, they are. They're very complex, especially when you're dealing with turbulent flows. Turbulence is characterized by all this chaotic, swirling motion at many different scales, and that makes the equations incredibly difficult.
So you can't just solve them easily on paper.
For most real-world engineering problems, no way. Finding exact analytical solutions is pretty much impossible. And that's precisely why we rely on numerical methods within CFD to find approximate solutions.
Okay, so given how complex these Navier-Stokes equations are, especially with turbulence, how does CFD actually tackle them? I know there are different sort of categories or approaches within CFD.
Yes, that's right. Because of the complexity, particularly the challenge of turbulence, various numerical approaches have been developed. Each category offers different trade-offs, accuracy versus computational cost, the level of detail you can capture, that sort of thing.
Let's maybe start with direct numerical simulation, or DNS. The name sounds like it aims for the highest detail.
In principle, yes. DNS is the most high-fidelity approach. It aims to directly simulate all the scales of motion in a turbulent flow, from the biggest eddies swirling around right down to the tiniest scales where the turbulent energy eventually dissipates into heat.
All of it.
All of it. Which means the Navier-Stokes equations are discretized on a very fine computational mesh, and the simulations are run with extremely small time steps to capture all those rapid fluctuations.
Okay, that sounds incredibly accurate. What's the catch?
The catch is the absolutely immense computational cost. Turbulent flows have this vast range of length and time scales. Resolving the smallest ones accurately requires incredibly fine meshes and the computational power needed. It just skyrockets, especially as the Reynolds number, the key parameter characterizing the flow, gets higher.
So for most practical engineering stuff.
For most practical engineering applications where Reynolds numbers are usually very high, DNS is just far too computationally expensive. It's not feasible with current computers for everyday design work. It's mainly used for fundamental research into turbulence physics, usually in simpler flow setups.
Okay, so DNS is the gold standard for accuracy, but too expensive for most things. What's the next level down? I've heard people talk about RANS models.
Right. Reynolds average Navier-Stokes, or RANS. This takes a fundamentally different approach to turbulence. Instead of trying to resolve all those chaotic fluctuations directly, RANS models time average the Navier-Stokes equations. You basically smooth out the instantaneous wiggles.
Okay, averaging.
But this averaging process introduces new unknown terms. They're called the Reynolds stresses, and they represent the statistical effect of all those turbulent fluctuations on the mean or average flow.
So RANS models don't simulate the swirls directly. They try to model the effect of the swirls on the average flow.
Exactly. That's the core idea. And various Reynolds turbulence models have been developed over the years to approximate these Reynolds stresses, using different assumptions to close the equations.
Like what kind of models?
Some common ones you'll hear about are the standard K epsilon model, the RNGK model, and the realizable K model. There are many others too.
And the big advantage is?
They are significantly less computationally demanding than DNS, and also less demanding than large eddy simulation, or LES, which we'll get to next. That makes RANS models really widely used in industry for a broad range of flow problems. They're often the workhorse.
But because they rely on models and assumptions, their accuracy must have limits, right? They can't be perfect for everything.
Absolutely correct. RANS models are built on certain assumptions about how turbulence behaves, and their accuracy can vary quite a bit depending on the specific type of flow you're simulating.
For instance?
Well, the standard K model, for example, works pretty well for many general turbulent flows. But it can struggle with flows that have strong streamline curvature or flow separation or what's called adverse pressure gradients, situations where the pressure increases in the direction of flow.
So accurately modeling those Reynolds stresses for all possible situations is still a big challenge.
It remains a significant challenge in CFD, yes, but there's been a lot of really exciting progress recently using machine learning, ML techniques to improve the accuracy and reliability of RANS models.
ML again. How is ML being used with RANS?
Researchers are exploring all sorts of ML techniques, using neural networks, for instance, to directly predict the Reynolds stress tensor, or maybe just its anisotropic part, the part that describes how turbulence differs in different directions. The idea is to learn better closure terms for the RANS equations directly from high-fidelity data, like DNS results.
So using data to teach the model how turbulence really behaves in certain situations.
Precisely. And they're also working on developing physics-informed ML models. These try to incorporate known physical constraints of turbulence, like Galilean invariance, meaning the laws of physics look the same regardless of constant velocity motion, right into the learning process.
Making them more physically realistic.
Exactly. The goal is to create more robust, more generalizable RANS models that can handle a wider range of complex flows with better accuracy. And people are also looking at interpretable ML, trying to understand why these ML-enhanced models work better, not just that they do.
That sounds like a really powerful combination. Okay, so we have DNS, super accurate, super expensive. RANS, less expensive, uses models, getting better with ML. What about large eddy simulation, LES? Where does that fit?
Large eddy simulation, LES, sits in a middle ground between DNS and RANS, both in terms of accuracy and computational cost.
Okay, the middle path.
Yeah. LES also starts with the Navier-Stokes equations, but it applies a spatial filtering operation to them. Think of it like blurring the flow field slightly.
Filtering.
Yeah, this filtering separates the large-scale turbulent motions, the big eddies that contain most of the energy, and are more dependent on the specific flow geometry from the smaller scale motions.
Okay, separates big from small.
Right. The large scales are then directly simulated, much like in DNS, but on a coarser mesh, because you're only resolving the big stuff. The effects of the unresolved small scales, the subgrid scales, or SGS, are then modeled using what are called subgrid scale models.
It's a hybrid approach. Directly simulate the big energetic eddies and use a model for the influence of the smaller ones you filtered out.
Exactly. That's the core philosophy. The idea is that the large-scale turbulent structures are more important, more sensitive to the geometry and boundaries, so you need to resolve them directly. The smaller scales, on the other hand, are often thought to be more universal, more statistically similar across different flows, so maybe they can be modeled with reasonable accuracy using these SGS models.
And are there standard SGS models?
Yes, one of the earliest and still commonly used is the Smigorensky model, but many others have been developed since.
So LES gives better accuracy than RANS?
Generally, yes. For many turbulent flows, especially those with significant large-scale unsteadiness or separation, LES offers a significant improvement in accuracy over RANS.
But it still has challenges.
It does. It's still more computationally expensive than RANS. And it faces challenges, particularly at very high Reynolds numbers, in really complex geometries, and for flows that involve things like shock waves or chemical reactions. And even with SGS models, resolving the region very close to walls can still be computationally demanding.
Right, the near wall region. I think I saw something about wall models used with LES. What are those?
Good point. For turbulent flows bounded by walls, think flow in a pipe or over an aircraft wing, the velocity changes incredibly rapidly right near the surface. Resolving those superfine scales very close to the wall, even in LES, can become extremely computationally demanding, requiring a very, very fine mesh just in that thin layer.
So wall models are a shortcut.
Kind of. They bridge the gap between the coarser mesh you're using away from the wall and the wall itself. They essentially provide a model for what the velocity profile and the shear stress should look like right at the wall, allowing the LES calculation to be done on a coarser mesh in that near wall region.
Saving computational effort.
Significantly reducing the overall cost, yeah. This is especially important for high Reynolds number flows, like simulating the atmospheric boundary layer or flow around full aircraft. And guess what? There's also ongoing research using data-driven approaches and machine learning to develop better, more sophisticated wall models for LES.
ML pops up everywhere. Okay, one more category mentioned was reduced order models, or ROMs. What's the goal there?
Reduced order models, ROMs, aim to create simplified, really low-dimensional representations of complex fluid flow dynamics.
Low-dimensional, meaning fewer variables.
Exactly. Instead of solving the full Navier-Stokes equations on a mesh with maybe millions or billions of points, ROMs try to capture the essential behavior of the flow using a much, much smaller set of variables or basis functions.
How do they figure out what the essential behavior is?
Techniques like principal component analysis, PCA, or proper orthogonal decomposition, POD, are often used. They analyze data from high-fidelity simulations or experiments to identify the dominant patterns or modes in the flow. And then they create a simplified model that evolves in time using only these dominant modes. More recently, deep learning techniques, like autoencoders, are being used to learn even more efficient and potentially nonlinear representations of these complex flow patterns, leading to better compression and accuracy in the ROMs.
So the main driver for ROMs is getting computationally cheaper simulations, even if they're approximations.
That's the primary motivation, yes. ROMs can be incredibly valuable for applications where you need to run a simulation very quickly or run many, many simulations. Think design optimization loops, developing control systems for flows, or making real-time predictions.
Okay, that makes sense. So DNS, RANs, LES, ROMs, quite a spectrum of approaches. With all these different methods, there must be a ton of software tools out there.
Oh, absolutely. There's a huge ecosystem of both commercial software packages and open source options available today. Each has its own strengths, weaknesses, areas of specialization.
What are some of the big commercial names people might hear about?
Your sources mention a few prominent ones. Powerful, widely used codes like NSYS CFX and ANSYS Fluent are very common. Fluent was specifically mentioned in one source for those Ahmed body car simulations.
Right.
Star CCM Plus is another major player, a very comprehensive commercial package used across loads of industries.
And what about that crucial mesh generation step? Are there separate tools just for that?
Yes, there are dedicated grid generation software packages. Things like Gridgen from Pointwise or GridD Pro from Program Development Company. These offer really advanced capabilities for creating high-quality meshes, especially for tricky geometries.
But don't the big CFD packages also do meshing?
They do. It's worth noting that many of the major commercial codes like NSYS and Star CCM Plus have their own integrated and quite powerful mesh generation tools built right in. That definitely streamlines the workflow for many users.
And what about researchers, maybe in universities, developing new methods? Do they use these commercial tools?
Sometimes, but often they develop their own in-house research codes. These are tailored to the specific problems they're investigating or the novel numerical techniques they're exploring. There are also popular open source options like OpenFOAM, which offer a lot of flexibility for customization and development.
So the choice really depends on the job, the user's expertise, budget.
Exactly. Specific application, user needs, technical expertise, available budget, all factor into the choice of software.
This all points to a really vibrant and obviously very important field. So for someone maybe listening to this, perhaps a student thinking about their future, is it worth starting an academic journey in CFD right now?
Oh, absolutely. Without a doubt. As your sources clearly indicate, CFD is flourishing. There's strong demand for skilled professionals across a huge range of industrial sectors: aerospace, automotive, energy, biomedical, environmental. The list goes on.
So the job prospects are good?
Very good.
Yeah.
The ability to analyze and predict fluid flow behavior using these computational tools is a highly valuable skill in today's technology-driven world.
Okay, so if someone is interested, what kind of academic background should they aim for? What's the roadmap?
Well, first and foremost, a really solid foundation in mathematics is absolutely essential.
Calculus, algebra?
Yep. Strong calculus, linear algebra, differential equations. These are the fundamental mathematical tools you need to understand the equations and the numerical methods.
Makes sense. And then fluid mechanics itself.
Definitely. A strong grounding in the principles of fluid mechanics, understanding the governing Navier-Stokes equations, different flow regimes like laminar and turbulent flow, heat transfer, compressibility effects, the underlying physics.
And then the computational side kicks in.
Exactly. You need knowledge of numerical methods, understanding how techniques like finite difference, finite volume, finite element methods work is crucial for knowing how CFD software operates under the hood, and especially if you want to develop your own code someday.
So theory and computation hand in hand.
Absolutely, and practical experience is key. Hands-on experience with meshing software using commercial or open source CFD solvers, that's hugely beneficial. Getting exposure to the different turbulence modeling approaches, RANs, LES, DNS, understanding their strengths, weaknesses, when to use which one, that's vital for being an effective CFD practitioner.
Are there particular specializations within CFD that might be good to focus on?
Yeah, as you progress, you might consider specializing, maybe in areas that particularly interest you or have strong industrial demand, things like multi-phase flows, mixtures of liquids, gases, solids, or combustion modeling. Aerodynamics is a huge field, heat transfer applications, biofluid mechanics, which we talked about, or increasingly this intersection of CFD and machine learning.
Right, the CFD plus ML area seems really hot.
It is. And beyond the formal coursework, getting practical experience is invaluable.
How? Internships, projects.
Exactly. Research projects, internships in industry or national labs, even independent projects. Contributing to open source CFD projects can be a fantastic learning experience. Or even trying to develop your own simple CFD codes that really deepens your understanding of what's going on.
It sounds challenging, definitely requires a diverse skill set, but also really rewarding.
It certainly is. It blends deep theoretical understanding with practical computational skills. But being able to understand, predict, and ultimately control fluid flow is just such a powerful capability with incredibly broad applications.
Okay, you've mentioned it several times now, so let's really dig into it. The future of CFD and this increasingly tight relationship with machine learning. Why is this combination, CFD plus ML, generating so much buzz? Why is it so significant?
Yeah, the integration of machine learning with CFD is arguably one of the most transformative and rapidly evolving areas in the entire field right now. It's really exciting.
Why? What's the big deal?
Well, ML offers the potential to tackle some of the long-standing limitations of traditional CFD methods and to significantly enhance its capabilities, making simulations faster, more accurate, and allowing us to tackle problems that were maybe too complex before.
Okay, let's break that down. How is ML helping to accelerate CFD simulations? We know computational cost is often a major bottleneck.
Exactly. That's a prime target for ML algorithms, especially deep learning models like convolutional neural networks or CNNs.
The image recognition things.
Sort of, yeah, but applied to flow data. Mm-hmm. They're being used to speed up the really computationally intensive parts of CFD solvers. For instance, researchers have shown that CNNs can potentially solve the pressure Poisson equation in DNS, which is often the most time-consuming step, significantly faster than traditional iterative methods.
Wow.
Other data-driven methods are being developed to accelerate how quickly pressure correction steps converge in standard solvers, like multi-grid methods. And ML techniques are even being applied at a higher level to optimize how we use high-performance computing facilities for running these massive CFD simulations more efficiently.
That's pretty impressive. What about improving the accuracy of the models themselves, especially for tricky things like turbulence?
Yeah, this is another huge area of focus and maybe even more impactful in the long run. As we discussed, accurately modeling turbulence, particularly with RANs, is a major challenge. So ML techniques are being used to learn better, more accurate, more generalizable models for those Reynolds stresses in RANs. Learning directly from high-fidelity simulation data or maybe even experimental measurements.
Trying to capture the physics better.
Exactly. And going even further, developing those physics-informed ML models we touched on. Building physical laws and constraints right into the ML model's training process, ensuring the results aren't just data-driven correlations, but are physically consistent.
That sounds crucial for building trust in these models.
It is. And related to that is the push for interpretable ML models for turbulence. We don't just want a black box that gives the right answer. We want to understand why it's giving that answer, gain physical insight from the ML model itself.
And for LES, is ML helping there too?
Yes. Data-driven subgrid scale STS models are being developed for LES, again trying to learn better representations of the unresolved small-scale turbulence. And as we mentioned earlier, ML is being used to create more accurate and efficient wall models for LES, helping to overcome that near-wall bottleneck.
It really sounds like ML is weaving its way into almost every part of the CFD workflow. What about in reduced order modeling, ROMs?
Yep, benefiting ROMs too.
Mm-hmm.
Deep learning techniques, especially things like autoencoders.
Autoencoders.
They're a type of neural network good at learning compressed representations of data. They're being used to learn more efficient, often nonlinear, ways to represent the complex dynamics of fluid flow from high-fidelity data.
So creating even smaller, faster ROMs.
Smaller, faster, and potentially more accurate ROMs that can capture more complex behaviors than traditional linear methods like POD. This makes them even more suitable for things like real-time control or rapid design exploration.
Okay, one of the most intriguing concepts I saw mentioned was physics-informed neural networks, PINs. That sounds different. How do they fit in?
PNs are a really innovative and quite different approach, yeah. They represent a way to solve partial differential equations, like the Navier-Stokes equations, directly using neural networks.
Directly solve them.
In essence, PINs are neural networks that are trained not just to match some given data points, but also to satisfy the governing physical equations themselves. The equations become part of the loss function that the network tries to minimize during training. Whoa. So the network learns a solution that has to agree with both the data you give it and the fundamental laws of physics.
Exactly. It's learning from both observations and the underlying physics simultaneously.
That sounds potentially incredibly powerful.
It really does. It could allow us, for example, to reconstruct entire flow fields from just sparse, limited experimental data. Or maybe solve complex flow problems, even when we don't have huge amounts of high-fidelity simulation data to train on beforehand.
Are there examples of this working?
Yeah, the sources mention case studies for both incompressible and compressible flows, where PNNs have been used to infer velocity and pressure fields from just limited measurements, maybe data from a few probes, or even just density gradient information you might get from certain optical techniques.
This could really change how experiments and simulations interact, couldn't it? It has that potential, absolutely. It blurs the lines a bit. So overall, this synergy between CFD and ML, it's poised to tackle some of the really grand challenges in fluid dynamics that have been tough nuts to crack for decades.
Such as?
Things like performing accurate simulations of high Reynolds number turbulent flows, especially near walls, but at coarser resolutions than DNS or fully resolved LES would need. Developing turbulence models that are not only accurate but also robust and interpretable, and enabling much more efficient and scalable simulations on the massive computers we have now, and maybe even looking ahead to future architectures, potentially even quantum computers down the line.
So, the future of understanding and predicting fluid flows looks incredibly dynamic, driven by this powerful combination of CFD and machine learning.
It really does. It promises to drive significant advances across that whole vast spectrum of applications. We talked about designing more efficient planes and cars, cleaner energy tech, better medical devices, understanding climate and weather. It's hard to overstate the potential impact.
Well, this has been an absolutely fascinating deep dive into the world of fluid dynamics and CFD. Just to quickly recap the key takeaways.
Sure.
We've seen just how fundamental, how pervasive the principles of fluid dynamics are. They influence everything around us, from daily life to cutting-edge industry.
Right.
We've explored the power of computational fluid dynamics, CFD, as this incredibly versatile tool for simulating, understanding, analyzing these complex flows, offering huge advantages in design, optimization, cost effectiveness compared to just physical testing.
Yeah, a crucial tool.
And we've really dug into this incredibly exciting ongoing fusion with machine learning, how ML is poised to push the boundaries of CFD even further, making it faster, more accurate, capable of tackling previously intractable problems and unlocking whole new levels of understanding.
A real game changer in the making.
It definitely seems clear that there are tremendous opportunities, both academic and professional, for people venturing into this really dynamic field.
Absolutely. And, as our reliance on simulations continues to grow, designing and optimizing everything from the tiniest medical implants to the largest infrastructure projects, this continued fusion of CFD and artificial intelligence, it will undoubtedly play a pivotal role. It's going to reshape the future of engineering and how we interact with the whole fluid world that surrounds us.
Definitely gives you something to think about, something to mull over or explore further on your own.